Hey, what's happening, guys? So, welcome to Fire Workshop. My name is Lucifer, and I'm gonna be showing you a circuit that I just made. Now, this right here is a full adder and a full subtractor combined into a single circuit. This particular side right here, this is the full adder side. This right here is the full subtractor side. I have used 4 ICs in total. This one is a XOR gate. This one is an AND gate, and this right here, this one is an OR gate, and this is a NOT gate. Right here, I'm gonna be giving the inputs. So the 3 inputs are this violet corresponds to C, the white corresponds to input B, and the yellow corresponds to input A. This is for the full adder circuit. I'm gonna be powering it with my 5 volts lab bench power supply. So my lab bench power supply has been set to 5 volts. Right here you can see this has been set to 5 volts, and right now the circuit is drawing around 0.2 ampere of current. So that's insignificant amount of current because these ICs do not consume a lot of current. Right here I'm gonna be shorting. Now these are automatically connected to ground. All the inputs are connected to the ground if they're not connected to the 5 volts because of these pull down resistors that I have placed. Now this is what the circuit looks like from below. Now this might look like a complicated circuit, and indeed it is a complicated circuit to make on a permanent circuit board. So I've just made it on a perf board or perforated circuit board, but I guess it was worth it to make. So let's just show you all the logic combinations that are possible with this circuit. Now this right here, this LED will represent your sum. This LED right here will represent your carry. This is for the full adders that I'm telling you. In the next video, I'll be covering the full subtractors because otherwise it's just gonna be a very long video. First of all, let me just place this input. This is the input number A, the violet one, to 5 volts. So this rail right here is 5 volts. I'm just gonna place it at 5 volts right here. You can see the sum is 1. This is showing me a binary 1. So this already represents a binary 1 at the sum output. If I place any other input at 1, the sum should be 1, isn't it? According to the logic table. So right now the B input is at 1, the sum is 1. Similarly, if the yellow, that's the C input, is at 1, the sum is again 1. Now let's just go back to the A at 1. Now if I keep another input except for A, for example, let's just keep the B input at 1 also. So you can see right now the sum is 0, the carry is 1 because it's a binary equivalent of 2. 1 plus 1 equals 2, so the carry is 1. So the carry is 1 because it's 2 raised to power 1, so the sum is 2. Now if I just place any other, for example, let me just remove this B input, let me just place the C input at 1. So right now the A and C are at 1. Again you can see the carry is at 1. Now let me just place all the 3 inputs at 1. According to the truth table, both these LEDs should light up because the sum should be equal to 3. So let's just see. So I'm just gonna place the B input at 1 also, along with the A and C, and right here you can see the sum is 1, the carry is 1, which is a binary equivalent. So these are actually hexadecimal. So these actually represent the sum as 3 because 2 raised to power 0 plus 2 raised to power 1, so that equals 3. So these are binary, so 1 to 3, and that is also 3. So this is how the full adders work, and these 3 ICs are responsible for carrying out the full addition. So thank you all for watching.